Hello students, welcome to this class of fluid mechanics. So in last class we have studied about velocity potential function, right? This class is about velocity stream function. So first of all, let's understand that this is also a scalar function, right? Velocity potential function was also a scalar function and velocity stream function is also a scalar function. So basically, first of all, let's understand what is this stream function. So we know that whenever a fluid flows, it flows in certain laminas. Fine. What I mean by laminas, fluid flows in certain layers. Like there are fluid layers one over the another. There is a one layer, then there is second layer above it. Fine, like this. Like this one. This is my layer 1, this is my layer 2, and then this is my layer 3, and so on. There are various layers flowing one over the another, and each layer has a certain equation or certain function attached to it. That is called velocity stream function, right? Each layer has a certain function that is called velocity stream function for each layer. And now, first of all, keep in mind that velocity stream function is denoted by this sign. This is psi. Velocity stream function is denoted by psi. Fine. So here, as you can see in 3 colors, these are 3 different laminas. We have taken these laminas for this study purpose. Fine. We will study about velocity stream function through these 3 laminas. Let's say my lamina 1 has velocity stream function associated with this as psi 1, lamina 2 as psi 2, and lamina 3 as psi 3. First of all, let us see what is the basic equation for velocity stream function, right? So first of all, del psi by del x is equal to v. V is velocity in y direction. Next is del phi by del y is equal to minus of u. What is u? Velocity in x direction. So this is my equation in Cartesian coordinates for velocity stream function. Fine. Now there is one more very interesting concept related to velocity stream function. That is, let's say here I have lamina 1, lamina 2, lamina 1, lamina 2, and lamina 3. Now let's say the distance between two laminas, lamina 1 and lamina 2, is b. This one. The distance between two laminas is b. So what is interesting? The difference between both the functions psi 1 minus psi 2 multiply by the distance between them gave us the flow rate. What is the flow rate? Fine. So psi 1 minus psi 2 multiplied by distance between both the laminas will give us the flow rate between both the laminas. Or you can say psi 1 minus psi 3 multiplied by distance between these two laminas. Let's say here this distance is a. Fine. Then what will be the flow rate between psi 1 and psi 3? It will be psi 1 minus psi 3 multiplied by a plus b. That will give us the flow rate in meter cube per second. Fine, in meter cube per second. And psi 1 minus psi 2 will have dimensions of meter square per second. Clear? I hope velocity stream function is clear to you, and you are also well versed with the fact that the difference between both two stream functions gave us the flow rate. The difference between two stream functions multiplied by the distance between both the functions give us the flow rate. So let's now study how this equation behaves with my steady incompressible flow. Fine. For continuity equation and for irrotational flow, as we have studied in velocity potential function, we are going to do the same study here in velocity stream function. So what is the continuity equation for steady incompressible flow? First of all, please keep that in mind that velocity stream function exists in 2 dimensions only. So I have written here the equation for continuity in 2 dimensions only. That is del u by del x plus del v by del y is equal to 0. Fine. I hope you understand this equation. We have already discussed it in the earlier class. The class I have taken on continuity equation. If you have not attended that class, first attend that lecture. That is available in this playlist only. Fine. First attend the lecture on continuity equation, then came back here. Continuity equation in 3D. Yeah. So here del u by del x plus del v by del y is equal to 0. That is my continuity equation for steady incompressible flow. So let's now replace the values of u and v here. What is my u? U is minus of del psi by del y, and v is del psi by del x. So when I will replace these values, I will get this. I will get one term here minus of del square psi by del x del y, and one term as del square psi upon del x del y. Now these both are equal and opposite in sign, and both are in addition, so it will turn out to be a 0. So what's interesting here that if velocity stream function exists, then my flow came out to be continuous. It automatically continuity equation is automatically satisfying my velocity stream function. So I can without any doubt say that if my velocity stream function exists, it implies that my flow is a continuous flow. Clear? Let's move further. In rotation, now let's discuss about rotation. Now I have discussed rotation in one axis along, let's say, wz. What is wz? Wz is equal to half of del v by del x minus del u by del y, right? Now here again I will put the values of v and u, and it will came out to be half of del square psi by del x square plus del square psi by del y square. Fine. It can also be denoted by del square psi. Now this is what Laplace equation says? Laplace equation says del square psi is equal to 0, right? Del square psi is equal to 0. So I can say if my flow is irrotational, then this thing should be equal to 0. Wz is equal to 0 if my flow is irrotational flow. So I can say that if my stream function satisfies Laplace equation, then flow will be a irrotational flow. If my velocity stream function is not satisfying Laplace flow, the flow will be a rotational flow. If it is satisfying Laplace equation, it will be a irrotational flow, right? As we can see here, this has to satisfy Laplace equation, because if it satisfies Laplace equation, it will implies del square psi is equal to 0, which will further imply omega z will be equal to 0, which will tell us that the flow is irrotational flow, as the rotational element is missing. Clear? So I hope you are very clear with the concept of rotation and the concept of continuity equation for velocity stream function. Actually here in velocity stream function, these both equations is condition for continuous and irrotational flow is opposite to velocity potential function, right? Here if velocity stream function exists, it implies flow is continuous. If velocity potential function exists, it implies flow is irrotational. And similarly, if velocity stream function satisfies Laplace equation, it implies flow is irrotational flow. And if velocity potential function satisfies Laplace equation, it implies flow is continuous. I know it's quite confusing, but yeah, if you hear to me again and again, you will understand that what I am saying. Fine. So I hope velocity stream function is clear to you, right? We have studied what is velocity stream function, how the distance between both the stream function multiplied by the difference between the difference of to both the function gave us the flow rate, and then we write the basic equation and its relation with continuity equation and irrotational flow. Fine. Yeah. Please do like and share if you like the video, obviously, and if you have any doubts, you can always contact me. You can post it in comment section. Fine. Well, see you in next class. Bye bye.